Hello, Calculus crew. This is David Peterson. I received a great question today, and the question was this: regarding our calculus work that we've done with a example where an object was tossed into the air, can we use our kinematic equations? And the answer is yes, absolutely yes. We can use our kinematic equations. There was another question, and this one I thought was very clever as well. Actually, it was from the same individual, but they asked, how about conservation of energy? Can I use that as well? And yeah, that's also a yes. And so I thought I would throw together a little video demonstrating how we can continue to use what we know and certainly build our knowledge base as we look at our calculus skills. So I dug a little and I found a video on YouTube, and let me just make this a little bit larger here. There we go. So this is what I had found. I found a stone is thrown vertically, and it wants us to find when it reaches the bottom of the cliff. And I'll go through this problem using calculus, our kinematic equations, and our conservation of energy. So you can see how we will be able to answer all of these questions with different strategies. So first up, let's take a look at, I'm going to set the kinematic equations and our conservation of energy aside. I'm going to answer this question by way of calculus first. So, looking at the problem, we are given, actually let's make this a little bit bigger here. There we go. We're given a stone is thrown vertically and it's thrown upward. So it's not just dropped off the edge of this cliff. It's thrown vertically with a speed of 17.8 meters per second. So I'm going to use V naught is 17.8 meters per second. Now that's upward, so I'll leave it a positive value. The position, the initial position, I'll use a S for our position, is 75.0 meters. And we're supposed to find, we're going to answer a few questions. How much later does it reach the bottom of the cliff? Well, no worries. I'm going to take advantage of our acceleration is negative 9.8 meters per second. And so I'll maybe make that statement right over here. Our acceleration is negative 9.8 meters per second, or per second squared. So if I address a function for any time t, hey, it's always negative 9.8. We have this constant acceleration. But here comes our calculus. What I'm going to do is I am going to integrate our acceleration function to get the velocity function. So I'm going to do that. I'll just do that right, maybe right over here. I'll use my pencil for some scratch work. I'm going to integrate the acceleration function with respect to time in order to get my velocity function. So I am integrating negative 9.8 with respect to t, and of course that's a negative 9.8t plus some constant of integration, which is the velocity at time 0, which in this problem is 17.8. So I'll put in a little 17.8. That's the constant of integration, and with a little calculus we now have our velocity function is equal to negative 9.8t plus 17.8. Grabbing my pencil for a little more scratch work, we can integrate our velocity function to get our position function. So I'll just do a little integration here. Our position function, oops, find an eraser. That was actually more workout than I suspected, finding an eraser. I must have been tough on the erasers this semester. Our position function, we're going to integrate our velocity function. Integrating negative 9.8 t plus 17.8. So we'll have negative 9.8 divided by 2 is negative 4.9, and then I have a t, which was to the 1, now it's 2. Alright, I think we got it. Negative 4.9 t squared plus 17.8 t plus some constant of integration, which is our initial position of 75, like so. So now that we've got it, we've got a position function as well. Negative 4.9 t squared plus 17.8 t plus 75. There we go. We got all the functions we need to answer any of the questions that they're going to throw our way. So let's go take a look. I'm just going to make sure I have my position functions. We're going to answer this using calculus first. Alright, so how much later does it reach the bottom of the cliff? To answer this first question, I'm going to say the position is going to be 0. If I have declared it at 75 meters high initially, we're going to look for when it's 0. So grabbing my position function and setting that equal to 0, let's take that position function. I'll just steal it right here. I'm going to title this question number 1. Question number 1. There we go. A little issue with zoom there. The position is 0. So I'm going to find where negative 4.9 t squared plus 17.8 t plus 75 is equal to 0. Now I'm going to use my quadratic formula to solve this. Let's just take a quick moment to do that. So I got two different answers for this. I'm going to record both of these answers and then throw one away. I've got a negative, so I got t equals negative 2.49704, but I'm already convinced I don't have a time machine, so I'm going to throw that one away. Let's go look at the next one. The other one that I found was t equals 6.1296966, and that's in seconds. I'll probably adopt the significant figures given in the problem of 3 and call it 6.13. The video that I found did that as well. 6.13 seconds is our answer for that first question. So let's just tidy that up. T is about 6.13 seconds. And we did that by using our calculus. Question number 2 is asking for what's its speed just before hitting. So number 2, I'm just going to make a note. Speed is going to be the absolute value of our velocity. So I will use my velocity function, and of course when it hits the ground it's on its way down, so it's going to have a negative value. I just have to put this 6.13 in there for t, and it'll give me the velocity, and then I'll just take the absolute value of it. And grab my calculator for this job. Now I have that 6.1296 and some change in the calculator. Just for fun, I'll store that to t. There we go. Stored to t. Now when I say t, it knows what it is. So when I look at my velocity function, which is negative 9.8 times t plus 17.8, and I put that into my calculator like this, I'm just going to use this velocity function. Negative 9.8 t, remember we stored t, plus 17.8. And we find then the speed, actually let's look at that a little closer here. The speed is 42.3. I'm going to write down the velocity as negative 42.27. I'm going to do that. So v of that t that we had stored, 9.8 t plus 17.8, when we put that t value in, this one right here, we ended up v of this 6.13 is about 40, I forgot what it was now, negative 42.271, and that's in meters per second, velocity in meters per second. So as we make a note on the speed, we'll just take the absolute value of that, and we'll say the speed then is about 42.3 meters per second, like this. There we go. Gosh, this calculus makes it pretty smooth. Well, we can do this one pretty easily as well. It's asking for total distance, and you know, if it had displacement, we would know the total displacement is going to be negative 75 meters because it dropped down, hit the ground at 75 meters. So if it said displacement, it's going to be negative 75. But it asks for total distance, so we have to account for, you know, the stone going up and then coming back down and then all the way down till it hits the ground. So we are going to integrate our speed function, and speed is the absolute value of velocity. So what we're going to do for number 3, we're going to integrate our velocity function, but the absolute value of it, so we can have our speed function. From 0 to that time 6.13. Now I have it stored in the calculator as t, so this will be very, very easy for us to do. I'm going to put my absolute value of this function, negative 9.8, I'll use x, I know it was t in the problem, but plus 17.8, and that's all in absolute value brackets. There's the absolute value of this function, and I'm going to graph it. Let's use a window. We know it hits the ground in 6 seconds, so let's go from like negative 1 to 7. I always like to see just a little bit more than I'm looking for, and I'm going to use a zoom fit. A lot of options here, but you can come up with, now the velocity function actually goes right through this t-axis and keeps going down like this, but when we take the absolute value of it, anything that's below is flipped up here, and we're now going to integrate from 0 over to 6. So second, calculate, integrate, which is number 7. Let's go from the lower limit of 0 seconds over to that 6.13, but I have it saved as t right in there. Let's save all the rounding for the end. So it looks like the total distance that it traveled was 107.33. And that's meters. Let's go 107 meters. That way we have that. Did I use 3 significant figures in these? Yeah, that'll work. There we go. So that's using our calculus. And we did that in about 14 minutes from start to finish, all those problems. Calculus, real smooth. What we'll do now is we'll look at, can we use those kinematic equations? And we absolutely can. In fact, the video that I was referring to here, if we push play, we can watch how this the author of this video did use the kinematic equations, and we'll get the exact same thing. We have all our answers, but this time we're going to look at it using our kinematic equations and then also our conservation of energy. So we'll have our kinematic equations handy. Here they are, and you'll see these in many different notations. You know, I like to use, you know, the initial velocity v naught. Here they have v subscript I and so forth. You'll see some different differences there. This distance here is expressed as d. Sometimes we'll see delta y. And, I just grabbed these. You are probably familiar with your kinematic equations. We already have our answer, so if you're only worried about getting the answers with your calculus, you're done here. But if you wanted to see the answer to that great question that I had, keep following along with this. I'm going to take the same problem and use the kinematic equations. And I like to have a picture, as you're all well aware of that. I'm going to take question number 1. How much later does it reach the bottom of the cliff? Well, I don't know. I'm going to call this question number 1 again. I know that it starts out at 17.8 meters per second on its way upward. It was thrown upward. It wasn't just dropped off that cliff. So I think what I'll do is I'll sketch a quick little picture of something that's going on here. I can keep track. Now this is my t-axis here, my time axes, and I'll just put arbitrarily here it starts out at 75, and as time goes along the object goes up and then comes back down and eventually hits the ground. Boom, right here. But I don't know any of the time. I just know that it started out thrown into the air at 17.8 meters per second. So this will be our initial velocity. Now I'm going to use that notation that I saw on my kinematic equations right here. And we'll figure out which one we're going to need. The initial velocity, v subscript I. I also know that acceleration is equal to negative 9.8 meters per second squared. I'll make a little note of that as well. I have that information. And we want to know at what time it hits the ground. So what has to happen is the object has to start here at 75 meters in the initial height and rise up here somewhere until the velocity is 0 here. Right at the top, the velocity is equal to 0, and some time will pass until that happens right here. I don't know what that is. Question mark here. And I'm going to go find that. I know it initially starts at 17.8, and then its final spot, I'll just put a little f right here. That's a tiny little f, probably hard to see. Let me zoom in just a little bit. There we go. Now we're going to pick an equation that has the information that we're looking for here. So as we look through our kinematic equations, we're looking for, what do we know? We know acceleration, we know the initial velocity, we're looking for time, we know the final, we know, here we go, this is what we're looking for right here. We have all that information. So we're going to find t. So let's go ahead and do that. We'll write this kinematic equation down. And then we'll put in the information that we have. The final velocity is 0 when it starts at 17.8 meters per second. Acceleration is 9.8 meters per second squared times some unknown t value. That's the time interval from here to here. So we'll solve that for t. So that's a negative 17.8 divided by a negative 9.8, and we get 1.816 seconds. That's this time, 1.816 seconds to 3 decimal places. Now it is true, because of the symmetry of our parabola, that when it was going 17.8 meters per second here initially, it's also going 17.8 meters per second here also, but now it's going down, so we'll use a negative value. 17.8 on the way up, now it's on the way down, and by symmetry, this time interval here, that was 1.816 seconds, is, let me see if it looks approximately right, same as right here. That's also 1.816, 1.816. So I'm just going to multiply that by 2, and we've got all the way over here. All we have left to find then for the time is from here over to here. And we don't have that yet. So hang tight. We're going to find it. We'll have to do a little more work, though. We just don't have enough yet. If we knew what the velocity was right here, we could call this the final velocity, and then this one the initial velocity, and we could recycle that equation. So as we look at our kinematic equations, we do have this distance right here. It's got to drop down 75 meters from here to here, that distance. I'll just put that difference from here to here has got to drop down 75 meters. We have the initial velocity here. We know acceleration. Hey, look at this. If we grab this next equation right here, we could use this one, this kinematic equation, to find that final velocity. So I'm going to use this kinematic equation right here next. So I haven't even answered question number 1 yet, but what I'm going to do now is I'm going to say this right here will be my velocity final. This one's out because I'm done with that. This is my velocity final. My initial velocity, V naught, I'm going to talk about this one right here. So from here to here, put that information in. Final velocity, well, I don't know, but I can find out because I know this is negative 17.8. I'm going to square it. Plus 2 times this negative 9.8, our acceleration, and our distance of negative 75 meters. It's got to drop down 75 meters. Let's go find the answer to this. I did type this into the calculator, and I got a final velocity of 42.27 meters per second. Remember, I took the square root of it. So I do have positive and negative. The velocity is negative. It's on its way down. So the final velocity is negative 42.27 meters per second. That's what this negative 42.27 is on its way down. But now that I have that, I can use this kinematic equation again. I know the final velocity, the initial velocity, the acceleration. Now I just have to solve it for time. So I'm going to use this one and put that information in here. So I'll write that kinematic equation down. Like this. I'll put in the information that I know. We'll solve this. I solved for t, and I got a 2.5 seconds roughly, 2.497. I'll write it down like that. And that's this time from here to here. This is not drawn to scale, by the way. So all we have to do is take 2 of these 1.816s plus this 2.497, and we'll be good to go. Plus 2 times 1.816, 6.13, a little touch of rounding in there, but the total time then, that was our answer for number 1. We had to take this 2.497 plus 1.816 1.816 plus another 1.816. Then we got total time. Time was 6.13 seconds. We'll notice that does match the work that we did with our calculus. Right here, we got that same answer. All right. There's something here that I wanted to talk about right in, with all this work that we did right here, finding from this point right here down to this one. Just going to put a little asterisk right next to it. Well, actually, it's a star now. It's going to be an asterisk, but it's a star. Right here. This is where I thought that question today was so good. Could we talk about the conservation of energy? Now, if it had just been dropped from start here at 0 meters per second, then you could just say your energy before is equal to the energy after. The potential energy, which would be mgh, would equal the final energy, the kinetic energy, of 1/2 mv squared. Now I'm getting that from, you'll recognize this right here. This was that question today that I thought was such a great question. Could we use this? And if this were just starting out at 0 meters per second, then this would work directly. But it actually has some kinetic energy because it's moving at this negative 17.8 meters per second right away. But this is easy to account for with our kinetic energy. So I'm going to find the same 2.497 seconds, but a different way. So my answer here is going to give us the same information, but it's going to be a different way. And this is by conservation of energy. That was the question that I wanted to address. So I've written down, I've got the potential energy and the kinetic energy. I've got mgh equals 1/2 mv squared. I have to modify this just a little bit because the thing doesn't start out with a velocity at 0. So I'm going to modify this a little bit. It does have some kinetic energy at the very beginning, so I'll just add that to it. 1/2 mv squared. This is its initial. I'll just put an I right here, and that's what I'm going to use right up here. I'll just make this the initial velocity, and then the velocity final right here. Velocity final. Actually, what I'm doing here, I think I misspoke a little bit when I got kind of excited. I'm going to find the 2.5. I'm actually going to find the velocity, this final velocity that I had found earlier. I'm just going to find it using the conservation of energy. And I think that was the question that was asked. Can I use this? And so I'll add that kinetic and potential energy together, and by the conservation of energy, this should be a true statement. Now mass exists in all of these, so I could divide both sides of the equation by mass, and it just cancels out. I'll just go ahead and do that right here. I'm going to put in the information that I have. 1/2 times the velocity, the initial one squared, so negative 17.8, which is squared, minus 9.8 times the negative 75, that change that we're making here, and that needs to equal 1/2 the final velocity squared. So we're going to solve this, and that'll give us our final velocity. We just solved this a different way by using the conservation of energy. We'll take the square root. Now we do get the final velocity then will equal the same 42.27, or we called it 42.3 meters per second It is on its way down, so I should be careful to talk about the velocity. If I want to talk about the speed, I'll just take the absolute value of it. There we go. So I hope that answered the question. Can you use your conservation of energy? Yeah, you can. Now, it's a little bit easier if it was just dropped from rest, but if we wanted to go this route, we could certainly find it. So we have some redundancies here. Certainly, we answered this thing with our calculus, with our kinematic equations, and our conservation of energy. All right, well, we're almost buttoned up here, but we do have that one question left. What's the total distance it traveled? And the theme here was to use our kinematic equations. So let's take a look at this one. What was the total distance that it traveled? Boy, this equation right here looks like it's going to do the job, because now we know the final velocity, our initial velocity, acceleration. We're going to be able to answer this question. Let's see how we do. So I wrote down the kinematic equation, and what I'll analyze is from here up to here. So I'm going to draw that line right in here. I'm going to find the distance from here to here, and then so it'll travel up and it'll travel back down. So I'll add 2 of those distances in, and then I'll add in another 75 meters right here. I'll tally it all up, and I'm going to be in pretty good shape. So what I'll do is I'll say my final velocity. I'm going to put this one back in action here, because I'm going to look for when it goes from here to here. So the initial is going to be 17.8. Let's square it. The final is going to be 0. We'll square that one, plus 2 times the acceleration, negative 9.8, and then this distance right here. That'll tell us what that distance is. Well, there we have it. This distance right in here, this d, that distance is 16.165. So it goes up and it comes back down, so I need 2 of those. So I'll just multiply that by 2. 32 feet took care of going up and coming down. Then we got another, not feet, but meters. 32 meters, and then I've got another 75 meters that it's got to drop. So there we go. 2 of those D's, 2D plus the 75, we've got a total distance .107 meters. There we got it.